Hello and welcome to Train Signal. You are watching a lesson about Linux installation planning. Your Linux tool belt is probably feeling a little heavier than when we started. It should now include knowledge of hardware settings, the boot process, and how run levels determine what mode you'll run the Linux kernel in. Hopefully you spent some time really digesting this information, because now we'll move on to other topics, namely the hard disk. If you're an administrator, chances are you'll inherit an already functioning Linux installation. But just like the new Linux user, at some point you'll probably need to install the operating system from scratch. And where will the software be installed? Why, of course, on your system's hard disk. We know that the most basic function of a hard disk is to store our data for retrieval when we need to use it. So as we consider a new Linux installation, we need to begin thinking about the most efficient way to organize that data. Now, while you could theoretically whip out an installation disk and plunge ahead, it's best to take some time to understand the layout of the disk and how to best customize your configuration. That's where we'll spend our time in this lesson. As part of the installation process, you'll install what's called a boot manager, which we touched on in the boot process lesson. This is the screen that you and your users will see when your systems boot up. Then we'll talk about shared libraries and how they make Linux run like a well-oiled machine. If you're ready, let's begin with the hard disk layout. I'm of the opinion that every Linux user and administrator alike would benefit from installing Linux at least once, but preferably a few times. This is where test systems or virtualization software like VirtualBox will come in handy. I learned early on to adopt the build it, break it, and fix it mentality. This is really the best way to learn. So you're ready to install Linux, but before you begin, you'll need to spend some time designing your hard disk layout, namely partitions. Partitions essentially segment your hard drive, and doing so has quite a few benefits. First, you can install multiple operating systems. It's not uncommon to have multiple distros of Linux and Windows running on the same system. For instance, my personal laptop has a copy of Fedora, Ubuntu Linux, Windows Vista, and Windows 7. Another benefit is hard drive space management. Depending on the number of users you support, your Linux installation can balloon in size. Separating user data from system files is another best practice. If a data partition fills up, or worse, experiences a failure, your critical system files aren't impacted. The same concept also applies to security. Your system partition may have different, more stringent security controls or permissions than a partition with user data. The Linux partitioning scheme uses 4 primary partitions, 3 primary and 1 extended. Primary partitions are numbered 1 through 4, and logical partitions are numbered 5 and up. Now, gaps can appear in the primary partition numbers, but not with their logical counterparts. The master boot record, or MBR, also holds the primary bootloader, as we've touched on before. This, of course, is the first piece of code that the CPU executes when the computer boots up. MBR partitions have the following 1-byte type codes, and yes, you'll need to commit these to memory. 0C is the code for FAT partitions, or file allocation table. 05 is the code for older type of extended partitions. 07 is for NTFS. 0F is for newer extended partitions. 82 is for the Linux swap file, and 83 is for the Linux file system. But what if you have a disk that's larger than 2 terabytes? GPT is Intel's intended BIOS replacement for all x86 and x86-64 computers. GPT has 3 data structures: protective NBR, the header, and the partition table. For now, you just need to understand these concepts, but you won't need to get into anything further than that. And finally, we have the LVM, or Logical Volume Manager. This stands as the lone alternative to partitions. To use it, you take 1 or more partitions and assign them the partition code of 0x8e. You can then use these utilities, pvcreate, vgcreate, lvcreate, and lvscan, to manage what are called physical volumes. You can then access these volumes from the /dev/mapper directory. Now, this is a complex scheme and it's not supported by every distribution. So the obvious question is, when then would you use it? One example is if you want a file system that's easily resized. Other than that, just know that you probably won't run into this type of partition manager often. Next, let's move on and talk more about mount points. Let's take a look at the hard disk layout on our Ubuntu test system. Now there are two ways to view this data, from the command line and graphically. We'll take a look at the command line option first. To launch a terminal window, we go to Applications, Accessories, and Terminal. You'll need root access to execute this command, so at the command prompt, we'll type in sudo, sudo, which again is the command to obtain root privileges for Ubuntu. We'll type in sudo space parted, which is a program that's used to display this type of information. And we'll type in another space, /dev/SDA. Then we're going to end it with print, which will display the information on the screen. So again, we have sudo to obtain root. We have parted, which is the name of the program that can give us the information on our hard disk layout. We've got the hard disk that we have. Yours, of course, may be different. I know that mine is SDA. And then we end it with the print command. And hit enter. And we see our partition layout here on the screen. The first column lists the partition number. Then we have the start and end points on the disk, followed by the size of the partition, the type, whether it's primary, extended, or logical, and we've got the file system type, and any flags. The first partition is a primary partition of type ext4, and it's also the boot partition. Then we've got the second extended partition, which has a size of 593 megabytes. And finally, the third partition, which is number 5, is the Linux swap partition. Okay, now let's take a look at this information graphically as well. First, let's type exit to close out the terminal window. Then, from the main menu, we're going to click on System, Administration, and then we're going to do gparted, which is the name again of the program. Okay, once this information comes up on the screen, you can see that we have our partitions listed here on the left. Again, the type of file system, any mount points, size, and in the instance of the boot partition, it'll tell you what part is used and unused. And if you want to see additional information about another one of the partitions, you can double click on it. And we can see here that we have some info on our swap partition, SDA5. We've got the status, we've got the size of it, and some sector information. Let's take a quick look at SDA1. And we've got the size. We know that it's ext4. We have the path, it's SDA1. It's mounted at root. Actually, this is the boot partition. And again, sector information. Let's take a look at the extended partition as well. And we can see the same information for that. In Windows, separate file systems are assigned to different drive letters, like A: for floppy drive, C: of course for your hard disk, and D potentially for your CD-ROM. This is one of the ways in which Linux and Windows are fundamentally different. A Linux file system is presented in a single tree view with the root directory represented by a /, and each device, like a hard drive partition or a CD-ROM, has its own file system. Each partition or device is then mounted as a mount point in that tree, called most appropriately the mount point. That mount point then becomes a directory used to access that file system. And just like the hard disk layout, directory organization should be planned at the outset. Now, some directories are best split off into separate partitions, and over the next 2 slides we'll outline those. Now note that the sizes that you see here are only estimates, and depending on your system or your distribution, these numbers will vary greatly. For those of you coming from Windows, the swap partition is similar to the Windows swap file. Now swap isn't mounted, but serves as a sort of a helper to your system RAM, so that your computer can of course run more or larger programs. A separate home partition will hold user files and also ensures they'll remain untouched as you upgrade system files on another partition. Unlike Windows, many Linux users prefer to upgrade their systems by doing what's called a fresh install. And this will of course overwrite any existing data, so you can see where having a separate home partition will come in handy. The boot partition, as its name suggests, holds critical boot files. The user directory holds most Linux program and data files, and as such is sometimes the largest partition. Depending on the number of users you have, home is the one that could get a little larger. The company introduced in our course scenario does some application development. So besides the standard Linux programs they have installed, their administrators will often have to compile or build programs themselves. These programs are unique to their installation, and they will be stored in the user local directory. The opt or OPT directory will hold third-party or commercial program and data files. var is sort of a catch-all that holds miscellaneous, often transient files associated with day-to-day computer operations. This directory is typically seen with servers that use server-related files like mail queues. MNT is not necessarily a partition, but its subdirectories are used as mount points for removable media like CD-ROMs. And the /media directory has much the same functionality. What we've reviewed here are directories that could easily be placed on a separate partition, but there are a few where doing so would prevent Linux from functioning. These include etc, bin, sbin, lib, and dev. In a subsequent lesson, we'll cover how to create partitions and file systems. For now, you just need to understand that when planning your hard disk layout, you may want to consider moving these mount points to separate partitions. Let's switch back to our Ubuntu test system to take a look at the file system that we have set up there. First, let's go ahead and close out gparted. Then we'll open a terminal window. With Applications, Accessories, and Terminal. Now, as you can see here, we're in the user Veronica's directory, so let's type in ls just to confirm that. Right, and these are the directories for this particular user. But we want to look at the directories for root. So to do that, we're going to type in cd space / and hit enter. And as you can see, this changed from the tilde to the / to indicate that we're in root. So now let's go ahead and type in ls and hit enter. This provides a list of the file system that we have. And as you can see, we have some recognizable directories like bin, we've got boot, we've got home and etc, we've even got opt, see temp here, user, and var. And if you guessed that you can also view this information graphically, you guessed right. First, let's exit the terminal, close that out. Now the directories and icons that you see on the screen are fully customizable, and these are the ones that I've chosen to have on my desktop, and yours probably looks a little different. For now, let's go ahead and click on the home. And if you see here on the left side, if you see file system, we're going to click on that. And this gives you a graphical depiction of what we just saw at the command line. You see the same directories. You've got boot, bin, dev, home, and some others. So again, you find in Linux you can do things from the command line and also graphically. Okay, let's head back to the presentation. In our lesson on the boot process, we learned that the bootloader, which sits in the master boot record, or MBR, allows the BIOS to load the operating system, i.e. the Linux kernel, into memory. And there are two most commonly used bootloaders that you need to be familiar with, and they are Lilo and Grub. I warned you about Linux's colorful terminology, didn't I? Lilo stands for Linux Loader, while Grub stands for the Grand Unified Bootloader. At boot up, the bootloader will present a menu where you select the operating system that you want to load. The image on your screen is an example of a Grub boot menu. And as you can see, we have several Ubuntu Linux kernel options. Next, we'll take a more detailed look at these bootloaders, starting off with Lilo. Lilo used to be the default bootloader for many Linux distributions, but recently it's been replaced by Grub. Bootloaders are installed during the installation process. Well, previously in some distributions you could select which bootloader to load, but now Grub is installed by default, and that's probably the way you want to leave it. The image on the screen represents a sample Lilo screen. Now Lilo can also be installed on an existing system by typing in the words Lilo, lowercase, from a command prompt, but you first need to set up its configuration file. So let's talk a little bit about that. In case you happen to run across Lilo on an older system, you should still understand how to use and configure it. Its configuration file is loaded in etc/lilo.conf, and it has two sections, a global section and a per image option section. The syntax for each statement in this file is option equal value. The options are boot, which specifies the devices that contain the boot sector. Default sets the default kernel or operating system that you want to boot if the user doesn't make a selection. Prompt issues a boot prompt intended for user input. Timeout sets the time in 1/10 seconds that Lilo waits before booting the default kernel. LBA32 or large disk support enables Lilo to boot with disks where the partition is larger than 1024 cylinders. VGA sets the VGA text mode to use while booting. Root sets the root partition, and Read Only sets to mount the file system in Read Only mode. Now you'll find that the Lilo configuration file actually looks a lot like Grub's, and we'll take a look at an example in a moment, but for now just bear with me. The next section, the per image section, is for Linux kernels or other operating systems. The section also has a set of options that are set in what's called stanzas. The image option designates which Linux kernel file to use. Other indicates the partition will have its own bootloader. Label provides a name. And init-rd points to an initial RAM disk. Append passes other options like memory settings to Lilo. But what if we wanted to add a new kernel to our system? First, you'll need to obtain root access and then open up the configuration file etc/lilo.conf in your favorite text editor. You could then copy and paste an existing stanza and modify the appropriate information. You'll probably want to change the label line, and this must contain letters, numbers, or both, but no spaces. Then change the image line to point to your new kernel. And once you've made all the changes you want, save the file and exit the editor. Now while still logged in as root, you have to type in Lilo in lowercase letters. This will reinstall Lilo in the master boot record, and you'll see your stanza names echoed on the screen. Now I learned the hard way not to remove an image until you're sure the new one works. That way if you have problems, you can still log in using the older kernel image and troubleshoot. The Lilo command itself also has a few options. The first, capital C, space conf-file, tells Linux to use a configuration file other than lilo.conf. Dash lowercase t tests the configuration, not writing anything to the master boot record just yet. You often couple this one with -v to see more information about the changes that would be applied without actually applying them. And finally, -boot space boot dev specifies an alternate boot device. Again, Lilo isn't a bootloader you're likely to run into, but those pursuing certification should be familiar with its operations. Let's move on to Grub. If you recall from the last slide, when you modify the Lilo configuration file, you have to type the Lilo command to reinstall it into the master boot record. But with Grub, this isn't necessary, and that is just one of the reasons why Grub is now Linux's default bootloader. You may have also heard the term Grub Legacy. This refers to the older version and the one you'll need to focus on for the certification exam. There is a newer version of Grub, but we won't cover it in this material. Grub's configuration file is /boot/grub space/menu.lst, and that is a lowercase l, not a number 1. But some distributions may use a different file, for instance grub.conf. The big difference between Grub and Lilo is that you don't have to reinstall it after you make changes to the config file. When you reboot, the changes are automatically applied. Now, as I mentioned before, the config file looks much the same as Lilo's. Here's an example on the screen. But let's take a live look at that. Let's switch over to our Linux terminal. From Applications, let's click on System Tools and Terminal. Now for this command, we'll have to obtain root privileges, so let's type in su and the root password. Now from here, we're going to use the cat command again to display file contents. So let's type in cat space /boot /grub /menu .lst and hit enter. And you can see the contents of the file. Now here's something that threw me when first trying to configure my own file. Take a look at the line that reads root hd0, 0 right here. This line demonstrates a bit of an odd difference between the way Grub refers to disk drives. The Linux OS would refer to the same drive as HDA. So accordingly, Linux drive HDB would be a Grub drive HD1. This is an important distinction and one I'd really like to emphasize. Another point is that the drive is followed by a comma and a second 0. This represents the partition number, and the numbering starts with 0 instead of the 1 that Linux uses. So again, Linux's HD1 is Grub's HD0, 0. And that's not all. Grub creates its own root called the grub root. And this isn't necessarily Linux's root file system. Just remember that if you didn't create a separate partition for boot when you partitioned your hard disk, Grub's root will be used and includes the full path to refer to the root, usually /boot grub. But if you did create a separate partition, Grub's root partition will be the same as Linux's boot partition. Like Lilo, Grub has per image options. They are title, which again specifies the label, root specifies the root partition. Again, this is the /boot partition if you separated it. Otherwise, it's the Linux root represented by the /. The kernel option describes the locations of the kernel and any kernel options you want to pass it, like for instance RO for read only. init RD again specifies an initial RAM disk. Root no verify specifies a boot partition for operating systems like Windows, which Grub can't load directly. Chain loader says to give control to another bootloader. If you figured out that in order to add a kernel to Grub, you need to edit the menu.lst file, you're right. You need to obtain root or admin privileges, open the file in your favorite text editor, and essentially perform the same steps we did for Lilo. You copy the stanzas, make any changes, and save. The only difference again is that you'll need to reboot to have the changes take effect. You won't have to reinstall. Now Grub again will probably be installed by default, but to install it manually, you use the command grub-install --device. So for instance, grub-install /dev /HDA will install Grub into the master boot record of your first hard drive. You can make Grub edits in the configuration file or on the fly. When you boot up and the Grub menu appears on your screen, you can use your arrow keys to move up and down the kernel listings, and pressing E will allow you to edit that kernel option. Now that we've covered Linux's bootloaders, let's move on to our last topic, shared libraries. Programmers are familiar with the idea of a library. Basically, it's meant to make their lives easier through sharing commonly used program fragments. A popular Linux library is called the GIMP Toolkit. or GTK+, which contains on-screen widgets used by programs, things like buttons and scroll bars. Under one scenario, library routines can be linked directly into the program's main file. But this would mean very large file sizes duplicated across every file that needed to access that library. This problem gave birth to the idea of shared libraries. Under this scenario, programs reference the shared library files that they need when they need them. Windows uses DLLs, or dynamic link libraries, similarly. But in order for programs to use library files, they have to know where to find them. For that, we use the library path. You set the path in the etc/ld.so.conf file. Let's take a quick look at the contents of that file. Let's type in clear to clear the screen. Then we're going to type in cat /etc/ld.so.conf. Hit enter, and you can see that only one line appears, and that says include ld.so.conf.d/**.conf. This line uses the wildcard character asterisk to say load all the files in etc/ld.so.conf.d whose names end in conf. Now you probably won't need to change the library path, as package files usually install themselves in directories on the path or can automatically add their own paths. If you happen to install a library package or program that creates its own libraries, like those you compile from source code, in an unusual location, you may need to alter the path. If you need to temporarily change it, you set the ld_library path environment variable. This variable simply tells Linux where other library files may be located. The common syntax is export ld_library_path equals the path. Each directory that you indicate on this line must be separated by a colon with no spaces. Now the first thing we should probably do is see if there's anything set for the current library path variable. And we do that with the echo command. So at the command prompt, let's type in echo space followed by the name of the variable, including the $sign. So we'll put in $, ld_library_path. Echo ld_library_path. And let's enter. And we see that we don't have anything currently set. So to change, again temporarily, to change the contents of that variable, we use the export command. So let's type in export space, variable name with no $sign this time, ld_library_path, followed by the equal sign, and let's set a temporary path at etc. And let's hit enter. Now let's use the up arrow key to go back to our echo command. Let's see if the new path is set. Hit enter, and we can see that the new path is set to etc. Okay, let's go back to our presentation. Now what if a program won't run and reports the problem as being due to a missing library? You first need to find out which libraries the program uses, and you do that with the ldd command, which can be run either as root or a regular user. The most used option for this command is -v, which displays a list of version info following the main entry. Now, first thing that we need to do is to pick a program to try out, and we're going to need to know the program's location. So I'll pick the gedit text editor. So to use the command, we type in ldd. We're going to use the -v option to get all of the information. And then I'm going to type in the full path to the gedit program, which I know is /usr/bin/gedit. Let's make sure we have that typed in. LDD-V for verbose user bin gedit. And hit enter. And what we have is a rather long listing of libraries that gedit is currently using, along with the full path. Now technically you could use this information to figure out what's being used so that if you find something missing, then you can add it. Okay, let's go back to the presentation and talk a little bit about the library cache. As you know, your internet browser can store cached versions of websites you frequent for faster, later retrieval. The Linux library cache works similarly. It uses a cached version of files and directories stored in binary in etc ld.so.cache. But the cache must be reloaded when you make any changes to the file, and you do so using the ldconfig command. Though you won't often need them, there are of course some options. -V displays the file updates as they're done. -N updates symbolic links, but not the cache. -n updates links in specified directories. -X updates the cache, but not the links. -F space CONFFILE says to use a new configuration file, where confile is the name of that file. -C space cache file changes the cache file ldconfig creates, where cache file is the name of that new file. -R space dir says to read the directory as if it were root, and -P will display the current cache. Let's head back to our terminal window and try out this command. Let's type in clear, and then we'll type in ldconfig ldconfig space dash lowercase p and hit enter. And as you can see in this rather long listing, you can see the library files ending in SO and their locations. You'll most likely breathe a sigh of relief to know that that concludes this lesson. As evidenced by the plethora of material we've covered in this lesson, you can deduce the importance of planning your Linux installation. In this lesson, we began with a look at the Linux hard disk layout and partition schemes. We talked about the various mount points and how to properly organize these directories from the outset and how it can help you better manage your system afterwards. From there, we covered bootloaders, learning that Grub is now the default, but that on occasion you may run into Lilo, and that you should be very familiar with how to install, configure, and interact with them both. We wrapped up with a look at shared libraries, where the files are located, and how to manage them. Thank you for watching, and I'll see you in the next lesson.